In this video, I'm going to start talking about infrared spectroscopy. And so this video will be mostly covering the theory behind infrared spectroscopy. The next video is where I will actually start talking about how to read the spectra and how to determine what the functional groups in your molecule are based on the spectra. And so in infrared spectroscopy, what we're doing is measuring the molecular vibrations using infrared light. So there are three different kinds of transitions we can do when we are looking at the interaction of atoms and molecules with light. And so there are electronic transitions, which is going from, say, the ground state to the first excited state, and that we can use UV vis spectroscopy for. There are rotational transitions, which happen in the microwave range. And then there are the vibrational transitions, which happen in the infrared range. And those are going to be the ones that we are interested in here for infrared spectroscopy. And so infrared light is here, it's in the longer wavelengths than visible light. And so it has less energy than visible light, which is why it doesn't do a full electronic promotion, like the transition in the UV and visible light is a full electronic transition. So that's why these are only vibrational transitions. Electromagnetic radiation has these electric fields and magnetic fields. So it's looking at the oscillations of the electric and magnetic fields, which are perpendicular to each other, and both are perpendicular to the direction of propagation. So it's the electric field that we're mostly going to be concerned with here, since it tends to be stronger than the magnetic field, and that oscillation of the electric field is going to be the driving force for our vibrations in these molecules. And so we're going to be interested in the infrared radiation that lies in the wavelength range between 2.5 times 10 to the negative 4 centimeters and 25 times 10 to the negative 4 centimeters. And so that corresponds to around the 10,000 micrometer range. And so the units we use for this are called wave numbers, which are just the inverse wavelength. And so they are actually proportional to the frequency rather than the wavelength. And so we get that here. So we have the nu with a line over it. And so we just use this right here, this conversion factor, and put our micrometers here in the denominator. And so that's how we can get the wave number for it. So for instance, if we have a wavelength that's 4 times 10 to the negative 4 centimeters, which is 4 micrometers, that corresponds to about 2,500 wave numbers here. And so what we're doing when we hit our sample with the infrared light is the driving force, as I said, is the electric field. And so that will interact with these dipole moments, which is based on the charge of the two particles. So these will be atoms within a molecule, and then the distance between them. And this will cause a vibration on the spring that will have to do with the spring constant that I'll talk about here more in a little bit. But this is going to be proportional to the electromagnetic field that's coming in, particularly the electric field, and this K, this constant here that has to do with the nature of the bond between these two atoms. Like I said, when we hit this with the infrared light, it will cause a vibration along this bond that can then be read from the spectrometer. And so what we're looking at here are essentially two different kinds of vibrations. So these are just the extensions and compressions of these bonds, and they can be symmetric or anti-symmetric. And so symmetric just means that when this one is moving this way, so this atom M1 here is moving that way, then this atom M2 is moving that way, and vice versa. If this one's moving this way, then this one's moving this way. Where anti-symmetric means that when this one is moving this way, this one is moving this way. And so we end up with this moving in, and then this moving out in that direction. And so these springs are not actually springs, obviously, but these are what are called harmonic oscillators. And so we put these as the potential of a harmonic oscillator here, where it's dependent on these K constants here. A better potential for this would actually be the Morse potential, but since we're looking at vibrations that are way down here near the ground state, the harmonic potential is going to be a good approximation for this. And so we use the harmonic potential to model this. And so, like I said, this constant K is like the spring constant and determines the vibrational frequency of the system. So we have the new symmetric and new anti-symmetric, which are based on these. So we see we have the reduced mass here in the denominator. So the higher the mass of these two things, the lower the frequency will be. But the greater this K constant here, or these two K constants here, then the higher the frequency will be. So like I said, we are mostly interested in this symmetric and anti-symmetric stretching, but there are other types of vibrations occurring. So you can get this scissoring where these are moving this way or in the opposite direction in the plane, or we can get twisting of these back and forth. And the vibrational modes for those will mostly be in what we will call the fingerprint region of our spectrum. But as I said, I'll get more into that in the next video. All right, so what we're looking at is allowed vibrational modes here. And so this is what's going to allow us to pick out which types of frequencies are being absorbed, and that will tell us what types of bonds we have in our molecule. So for instance, if we have some wavelength of light that is too long, so too small of a frequency, then that's not going to be enough to promote it from the ground state to the first excited state here. And we can think of this in vibrational modes too, but this is just an illustration here. And so we need a photon of a certain wavelength here to actually get it to promote from the ground state up to the first excited state here. Then if we have another wavelength here that's somewhere in between the first excited state and the second excited state, then that will also not give a promotion. What we're interested in here is the fact that these are only going to be able to go to these various states at these certain levels. So things in between will not appear to be absorbed. So here I just show that this photon is enough to get it to the second excited state. And so those are the absorptions that we are interested in. So radiation is more likely to be absorbed at frequencies that match the energy difference between two quantum mechanical states of the molecules. So that's what these states are here. So when the radiation has a frequency, say, that matches the difference in energy from there to there, then it's going to be much more likely to absorb that. So the energy difference is based on this. So again, we see that K in the numerator there and the mass in the denominator there. For IR spectroscopy, we are looking at vibrational states of the molecules. So when a photon with the correct group frequency, nu, which again, we see that K here in the numerator and the reduced mass in the denominator. So when the correct group frequency is absorbed by the two atoms involved in a bond, and that bond will have some constant K, this causes the atoms to vibrate along that bond. And so, like I said, we're interested in the symmetric and anti-symmetric. When the photon is re-emitted, it often does so at different wavelengths due to emitting multiple photons of higher wavelength. So what I'm saying there is essentially, if we have our energy diagram here, we have our ground state and our first two excited states. So we might have it go up here and get promoted to the second excited state, and then when it relaxes, instead of going all the way down, it goes down by 2 or 3, I guess, as I put this as the ground state. So yeah, it can go down by steps that way rather than having to go all the way down at the same time. And so that's what I mean by the photon being at a different wavelength when it's re-emitted. And it does this in a random direction, and so no longer in the direction of the incident beam that's going into our sample. And the photon will therefore not be picked up by the detector behind the sample. And this shows up on the detector as a loss of intensity. So we can think about it this way. So we have our incident beam here. We have our sample here that will absorb yellow, and we have the beam coming out of our sample. So this is at 100. Each of these I put just as the same number, so 16.7. When it goes through the sample, all of these are 16.7 except for our yellow. So it has absorbed the yellow, and so the intensity here has gone down by the corresponding amount. And so that's how we would see this as an absorption, because we know how much light we're putting into it from the incident beam, and then we're detecting how much light is coming out of it. And so the incident light of wavelength lambda and intensity here, where the intensity is going to be based on the wavelength, strikes the sample and some is absorbed. The transmitted light of wavelength lambda has this intensity after being absorbed by the sample. And the relationship is given by the Beer-Lambert law. So if you've taken general chemistry, you've probably seen it in this form, but it comes from this. So we have the intensity of the light hitting our detector, and the intensity of the incident light is being equal to this exponential right here. So this has a negative in it, so that's why I flipped the intensities in this natural log right here. This natural log of the incident over the transmitted light is just the absorbance right here. And so that tells us how much is absorbed. And again, this is going to be based on the wavelength of light. And the reason it's based on the wavelength of light is because of this molar extinction coefficient, which is based on the wavelength of light. So if you look at the molar extinction coefficient for different wavelengths, so we might have this, so this is our epsilon, this is our wavelength down here. If you found the molar extinction coefficient for all these different wavelengths, you might see something that looks like this. And so it depends on the wavelength what the molar extinction coefficient is, where right here would be the highest molar extinction coefficient. And so that's why that is based on the wavelength. All right, so what this means though, putting the two things we've been talking about together, which is the vibrational modes and this absorption of frequency here. So we're looking at our atoms within a molecule vibrating, and there are two things, I mean there are many things, but two of the main things that are going to influence the vibrational mode are the K constant and the mass. So if we look at the mass, we see that this is going to be inversely proportional to our vibrational frequency, since the mass shows up in the denominator here. So if this is a higher mass than this, which is what we're showing here, then this is going to be a higher frequency than this. And so we can actually look at this with real bonds here. So a carbon to hydrogen has a wave number of 3,000 inverse centimeters. Then carbon to deuterium is 2,100 inverse centimeters. So remember, these inverse centimeters are directly proportional to frequency. They're inversely proportional to wavelength and directly proportional to frequency. So the larger number means a higher frequency. So this one, where we have the lightest element here bound to it, has a 3,000 wave number. When we have a deuterium, which is a heavier version of hydrogen, we have 2,100. And when it's carbon to carbon, we have 1,200. And so the frequency decreases with increasing atomic weight. And the other thing is this K constant here. So if we have, say, two springs bound to it, then we will have a larger K constant here than if we just have one spring bound to it. And so the bigger K is going to result in a bigger frequency, so a higher frequency. In these multiple springs, we can think of as being multiple bonds. So if we have a carbon-to-carbon triple bond, that's 2,200 inverse centimeters. A double bond is 1,660, and a single bond is 1,200. And we can look at that for carbon to oxygen as well. So if it's double bond, it's 1,700. If it's a single bond, it's 1,100. So the frequency increases with increasing bond energy. So that K is proportional to the bond energy for this. All right, so changing gears a little bit here. So now we're going to actually talk about the instrument that we're using to do this infrared spectroscopy. So one of the more popular versions of this instrument nowadays is called the Fourier transform infrared spectroscopy. And so this is going to use this, which is called a Michelson interferometer. So it has a stationary mirror and a moving mirror. We have our light source here. It's going to emit light that hits this beam splitter. This allows half of it to reflect and half of it to transmit. So the reflected will go up to the stationary mirror. The transmitted will go to the moving mirror. They reflect off those mirrors. They come back here, recombine, and then go down here where it will hit the sample and then be detected. And so the two beams traverse distinct paths and reunite at the beam splitter, where the combined beams are directed into the sample and detector. When two beams traverse the same distance, they are in the same phase. This is the zero path difference position of the movable mirror. And so what happens when these have the same path length is we get constructive interference when we finally get back here, because these are in the same phase. So as the movable mirror shifts away from the beam splitter by some delta x, the movable mirror beam travels further. This is called the optical path difference delta, and it equals 2 delta x. The reason it's 2 is because if we say move the mirror from here to here, the light has to go this distance, which is our delta x, but then it has to come back this distance, which is another delta x, and so that's why it's 2 times that delta x. So the beam splitter generates an interference pattern by merging the two beams. Constructive interference occurs when the optical path difference is an integer multiple of the wavelength. So when our delta is equal to some integer n times the wavelength, while destructive interference happens when the optical path difference is 1/2 wavelength, an integer multiple of the wavelength. So we put this half here, and we'll get a mixture of the constructive and destructive at phase differences between those values there. So in the case of a monochromatic radiation source, the detector captures the signal intensity of a cosine function of the optical path difference. And so this is saying for monochromatic light, but in our FTIR, we're often using not monochromatic light, but multiple wavelengths. And so we can have these multiple wavelengths here, where we see here we have some constructive interference. Here, 2 of them are constructively interfering, but 1 is destructively interfering, and so on. So it's this complicated mixture of these wavelengths here. And so for each of these wavelengths shown up here, intensity at the sample undergoes oscillations from full amplitude to 0 amplitude as the mirror is displaced. In the context of a Michelson interferometer, the movable mirror is shifted at a constant speed. So at a constant speed, this is important here, from one extreme position that we can just call plus x to another that we can call minus x. So that's just talking about that moving mirror moving. Following a relatively slow movement in one direction, the movable mirror is swiftly returned to its initial position, and then moved again to capture a second spectrum, which is combined with the first. And this second spectrum will be with the mirror moving at exactly the same speed. So due to the consistent fixed rate of the mirror's movement, the intensity of each of these 3 wavelengths varies over time, giving each wavelength a distinct time domain. And so because they're moving at the same speed every time, we can call the change in the phase differences a time domain for this. So the differing time domain properties of wavelengths, so we can call it x, 2x, and 4x. So we can call each of these, one of them is x. So maybe the green is x, the blue is 2x, and the red is 4x. Mean that the patterns of full and 0 amplitude for each wavelength are dissimilar. Like I said, we can see in some places it's fully constructively interfering. Other places it's somewhere in between. Other places here we can have 2 constructively interfering, 1 destructively interfering. The combined representation of all these wavelengths is called an interferogram. If a sample possesses the ability to absorb infrared radiation of wavelength X, for instance, the intensity of light at this particular wavelength diminishes after interacting with the sample, and this change is reflected in the interferogram. And so this is what an interferogram looks like right here. where we have our mirror position, which remember we can model as time since it goes at a constant velocity. And then we have the light measured by the detector here. And we see we get this sort of complicated pattern of wavelengths here. And so from that, we can do what's called a Fourier transform. I'm not going to talk about what that all entails here. I do actually have videos where I go into some more detail about that in my crystallography and in my cryo-electron microscopy videos. But what we care about for our purposes here is that we have this time domain, and so we can do a Fourier transform and put that into the frequency domain. And so the frequency, as I said, is being proportional to the wave numbers. And so we can sort of disambiguate all of these wavelengths here, and so that will tell us at what frequencies this is absorbing, because if it's, say, absorbing this frequency but not this one and not this one, then when we do this Fourier transform, we will find that, say, this peak would actually go away, even though, because we know what light we're putting out, we would expect one there, and so we would know that it's absorbing at that wavelength. So like I said, we have this interferogram here. We do it for the background and for our sample. We get spectra for both of those. We subtract the background off from the sample, and that gives us our absorbance plot right here. And so just kind of a sneak peek at what I'll be talking about in more detail in the next video. These are the types of spectra that we'll see, or at least where the peaks that we're interested in will be. And so a really important one is the C double bond O stretch. So that's the carbonyl stretch. Then we have the C to H on the alkyl CH stretch here. So that's on the saturated alkanes, then on the unsaturated alkanes here. So where saturated is to the right of this 3000, the unsaturated to the left, which makes sense. As I said, when we have those double bonds, that tells us that we're going to have that higher K, and so we will have higher frequency vibrations. And so that tells us that it's going to push it in that direction. And then, of course, we have the alkyne stretch here, which is even further to the left. Then we have our OH stretch and our NH stretch, and those are even higher frequency because we are now using these hydrogens, which are going to be they're going to be very light atoms. But we also have these large dipole moments here. So the oxygen to hydrogen bond and the nitrogen to hydrogen bond. And so that will give us those high frequency vibrations there. Then we have the C to N, C to C. So those do have the triple bonds, which would increase the vibrational frequency, but they're on these two different heavier atoms rather than the H's that we're looking at over here. And so that's going to reduce the vibrational frequency. Then we have the C to O double bond, which the oxygen is even heavier than carbon, so that's why that is shifted over to the right, to the lower frequency there. And so this is essentially the kind of peaks we're going to be looking for on our infrared spectra. And these tell us information about the functional groups that are in our molecule. And while this can be helpful in its own right, when we combine this to what I'll talk about in future videos, things like mass spec and NMR, this can be very powerful for determining what species of molecule we actually have in our sample. But anyway, that was everything I wanted to talk about in this video. I hope you found that helpful, and I will see you in the next one.